Good morning, everybody. If you have a question, put it in the chat and I'll go through it. All right. Okay, so we continue with 1.6. We're going to finish this guy. This is a basis and the dimension. So next week, right, she made a mistake in the announcement. So I will continue Zoom throughout the year. So we will always have Zoom. It's just some people wanted to do in person, so I will also do in person. So both, just to be clear. But yeah, we will also make an announcement. All right, let's go. Yeah, the Zoom will be the same time. So you can be at home. I will run the Zoom live. So you can ask questions, and I will also be in person because some people want in person too. So I'll have both. All right. All right. So we have now we talk about existence. So yeah, the prerequisite is you have a vector space, but you need it to be spanned by finitely many elements. Okay, there are counterexamples. So C01 has no basis, right? So not every vector space has a basis. So C01 is a vector space, It satisfies the axioms, but it does not have a basis. Okay. So this is special to this finite dimensional object. So it's not true in general. Yeah, this is finite dimensional. This just means what I wrote here means finite dimensional. You can also work for countable dimensional, like, we talked about it last time, the arbitrary degree polynomials. So here, this is the span of 1x, x squared, so on. Yeah, not in general. So what are we going to prove? We're going to prove that if you're finite dimensional and you can give me some linearly independent set, like suppose you have R10 and you give me S to be, 1, 0, 0, 0, and 0, 1, 0, 0, 0, then I can extend S prime to an S prime such that span of S prime will be R10. Does that make sense? So you start with at least a small core, and from there you can build to the whole space, which is kind of amazing to think about. But okay. Right. So for this, we need a lemma. We need this augmentation lemma, right? Because I started with this S with 2 vectors, and I need to go up to 10 vectors. So, so we bootstrap. So we start with this 2-element guy. We take a X, which is not in the which is not in the set S, and then you have the following, that if you add it to that set, then that set is Li if and only if X is not in the span of S. So let's go back to our example. So you have 1, 0, 0, and 0. Okay, so the element 2, 0, 0, 0, 0 is not in S, right? So indeed it's in V take away S, but do we have that S X is Li? Yes, no? Can I get a quick yes? Yeah, no. So the answer is no, because X is in the span of S. So you need something else. And as you can imagine, one simple example is you just have 0, 0, and 0 elsewhere. That's a good one. So that S of X or S of Y is Li. Okay. All right. So we did something like that before, but let's go over it again. So let's do one direction. Suppose you are linearly independent. Let's get that X is not in the span. Okay, this is the yeah, one of the directions. Right. So what am I writing here? No, so suppose by contradiction that X is in the span. This would be in, not in. So suppose X is in the span of S, we'll get a contradiction. Yeah, this is supposed to be in. Okay, but if it is, it means you can be given as a linear combination of elements in S, right? So that's what being in the span means. And what did we do? We added the additive inverse, added additive inverse to both sides. Okay, so we added this minus 1x. So x minus 1x is 0v. All right, so hopefully you can see it now. But this relation over here is just saying that the elements of Sx are linearly dependent because one of the coefficients, namely the A0, is not 0. So the moment you have that, you have linear dependence. That was the definition. That was definition of LD. This is the definition of LD. Okay.
I have a question about this.
Yes.
Yeah. In this case, like when we put the vectors into these equations like this, where we identify whether the coefficients are 0 or not, what would be the other ones, like A1 to AN?
Yeah, so the other ones could all be 0. Okay, so just to be clear, yeah. So, yeah, very good question. Thank you. Okay, what should I say here? So since we know X is in the span of S, there exists an AJ that is not 0. So all other ones could be 0, but there exists at least an AJ that's not 0. And so that means that you have the following. Suppose all others, just suppose that A0 is not 0, A1 is not 0, but then all the other ones are 0. Then you're left with what? Minus 1x and A1v1 equal to 0. So you get a relation between them. Even if,
Thank
in
you.
fact, it's even easier than that because 0 is always on in your span. So, and but okay, anyway, so yeah, your question was, what about the other coefficients? We can at least ensure that at least one of them will be non-zero because x is in the span. Yeah.
Okay.
Hello. Yeah.
If X was the zero vector, they would all have to be.
Yeah. If x, so how should I say this? Yeah, there's a little bit more work. You're right. So if x is the zero vector, then you're immediately done. Okay, because then s 0v is almost by definition um, the same set. So okay, how should I say this?
Yeah.
Okay, yeah, okay, but yeah, let me write it out because no, this is a good point. People usually skip it. I shouldn't skip it. So case one, suppose x is the zero guy. Then what should I say? Okay, so x is 0. Let me see. And yeah, we say that, what are we saying?
I think technically,
So okay, let me say the following. If you're in this case, this proof is different. So when x is the zero vector, then you have that x, that this is in fact in the span of S. It's in fact in the span of any vector, not just S, because you can always multiply your guys by 0.
mhm.
And so you do not have Li, but the assumption is that X is not in the span. So you get a contradiction. So it's sort of like immediate, like,
Mhm. Yeah, I see that one.
yeah. So like the thing is S0V is Li, assume X0V is what maybe I did want to say. No, I assume by contradiction that X, what do I want to say? Well, anyways, I mean, X will be in the span of S. So you added a linearly dependent vector. Yeah, so it's like immediate. Yeah, is that okay?
Yeah, thank you.
Are there more questions? Oh, I see they're all, okay, I see. What are they saying? V complement S just means take away all the elements of S from V. So I did an example over here. Where is it? So my S are these two vectors. Take V to be R10. So you simply remove these two guys. Yeah. All right. Where am I here? Yeah, so 0 is never in Li set because it's the yeah, I mean it's always in the span of any other vector. Yeah, exactly. Oh. All right, so let's recap. So yeah, if X is 0, it's immediate because X is in the span of S, so you lose Li. If X is not 0, then one of these coefficients Aj is not 0, otherwise you wouldn't be in the span. And so you get this linear dependence relation between them. All right. In fact, even here, I don't even need, I can combine the two proofs and say AJ. So, because the definition of LD, just to be, I'm overcomplicating stuff as usual. So, um, let me just write it like this, because this is really the definition of LD, is that at least one of them is non-zero. So it sort of contains both. If this zero stuff confuses you, let me say it again. We assume by contradiction that X is in the span of S, okay? That means you can write X in this way, all right? They could all be zero. They could all be zero. Zero is still in the span of any vector. And then you rewrite it like this, which is just the definition of LD. Was that Maria? I don't know who had the question. Is it
Yeah.
better? Okay, is
Yeah,
it better?
yeah, it makes sense. Thank
Okay,
you.
yeah. So, okay, good. All right. Yeah, now let's do the other direction. Suppose X is not in the span, assume by contradiction that it's dependent. Okay, so since, oh yeah, dependence. So since you have dependence, you have this guy over here where there's an AJ not zero. That's it. That's the only thing you can assume from LD, that at least one of them is not zero. And where do we go? Yeah, now here I have to split cases. So, right. Okay, so let's see. So again, AJ is not zero, some one of them. So case one, A0 is not zero, meaning the coefficient of X. And since you have that, use that for fields, when you have, A not zero, there exists a multiplicative inverse such that A inverse A is 1. So that's all I did. I started from here. I moved all these guys to the other side, and then I multiplied by the multiplicative inverse, right? So A0x is equal to minus A1V1 all the way to minus AMVM. And then I multiplied by the inverse. So X is equal to A0 inverse A1V1, so on, A0 inverse AMVM. Okay. All right. Good. So what does that mean when I do this? Well, it means that X is in the span of S because you wrote X in terms of the other guys. I mean, you can call this B1, call this BM. So you have B1 V1 all the way to BM VM. And each of them is in the field because the field is closed under multiplication. So you get that X in the span of S, which was our assumption that X is not in the span of S. Okay, so to be clear, we're proving S Li if and only if X not in the span of S. That's what we're proving. We did one direction like this. Now we're doing the other one. And we're assuming that X is not in the span of S. And we want to prove that when you adjoint X to S, you preserve linear independence. So suppose not, suppose you broke independence, even though X is not in the span of S. So we wrote it like this. This is the dependence condition. And then we just rewrote, we isolated for X. Okay. All right. Case 2 is that A0 is 0 over here. So you have 0 here because 0 f times x is 0v. We proved that last week. But then you get this condition over here. And by LD, you need, like we said, you need an AJ to be not 0. In this case, you could just take AJ to be A0. But here we have A0 is 0. So AJ is not 0 for some J bigger than 0. So it would be 1 to M. Okay. So that's what LD tells us, which is a contradiction, because if you know that AJ is not 0 here, then this contradicts LI, which implies that A1, A2 are all 0. Okay. Is that okay? That's the trick. Okay, so what does that mean in practice? Yeah, let's use it in our theorem. So just to remind you what we're proving, I'll write it here. So you have a V that's spanned by finitely many vectors, and you have an S in V that is Li. We claim that you can make it grow. There exists S prime that contains S, such that S prime is a basis. And that meant two things. S prime is Li, and span of S prime is V. We already know that span of S prime is V, right? Because span of S is within span of S prime, and they're both inside V. So you get span of S prime is V. So that's not hard. The hard part is that each time you add a vector, do you preserve Li or not? Each time you add a vector to get a basis. Okay, what am I saying here? No, you don't know this span condition. What am I talking about? Did someone hopefully correct? No, no, sorry, you don't know that S is in the, no. So all you have is that S is Li, that's all you know. And we want to span the set. And what I was thinking is you could have taken, in theory, you could just take V1 to Vn, but here we do not assume, okay, let me write like this. We don't assume that V1 to Vn are Li. Okay, we don't assume that here. They could be dependent, otherwise we're done. If we had that V1 to Vn are Li, we're done. We don't have to do anything. Okay, all right. Yeah, let's just go to the proof. Let's see what's going on here. Okay, so right, so these guys over here are, their span gives you the whole space. So you need that. You need to have a collection that gives you the space. Otherwise, there's nowhere to pick from. Okay, so you need that. And you know that S is what? It was V1 to Vm. All right. Now what do? We use our algorithm from before. So you look at U1 and you ask, is U1 in the span of S? If yes, ignore it. If no, add it. So write S prime to be S union U1. That's the basic step. If you have a question, please tell me, because that's the main thing. Okay, so That's the main algorithm. You start from the very first one. So you need to have something. You start from the very first one and you ask, is U1 already covered from your span? Yes, forget about it, add it if it's not in the span. So I1 is the very first occurrence. Let's say it could be like U10, right? It's the very first occurrence that is not in the span of the previous guys, span of S. All right. And we showed that if you can guarantee that, you can guarantee Li. That's because it's much easier to check something is in the span than it is Li. So that's basically the logic here. All right. So we continue. So now S, if you like, I don't know, 1, you let it to be S UI1, and then you ask for U2, like the very next one. So like UI1 plus 1. Is this in the span of S1? Yes, no, ignore it, add it. So you keep playing this game till you get the second guy, S2 equal to S, UI1, UI2, so on and so forth. So eventually you run out all the elements. So you run out through all U1 to UN. Okay, so there's no more vectors. And we get this entire set over here. And the question is whether you have span of S prime is V and whether S prime is Li. If you have this, you get your basis. Okay, all right, fine, let's go. So Li is easy because at each step we guaranteed Li. So this guy is Li, this guy over here is Li, and so on. So each time we were checking Li. So that means we never introduced a redundant vector. Redundant. These guys were all ignored. Okay, good. What about span? So let's do that. So we already know that span of U1 to UN is the whole space. So the question is how to use that information. Let's see. So so we got UI1 to UIK, right? Are in S prime. Now, what if UM is none of them? UIJ, one of these guys, J1 to K. What if you have this situation? Well, we ignored it, right? That was the point. We ignored it precisely when UM was in the span of the previous guys. So span of like this. So I mean, definitely span of S prime, but it was easier than that. It was in the span of V1 to Vn M. We call this R, not to confuse you. So this UR guy was in the span of V1 to Vm, plus whatever you added up to that point, I1, I2, say, if R is like bigger than I2, something like that. So that's the game we played, right? If it's not in our collection, we ignored it because it was in the span, right? That was the trick. So all the ignored ones were already in the span. All right, good. And that's it really. So we each UI was either in the set S prime or it was in the span of S prime. Therefore, V, which is the span of these guys, and we show that each of them is either in S prime or covered by the span. So it's within this span of S prime, which is by definition inside V. This is just because S prime is in V, so the span is also. We proved that last time. So yeah, you get that. You get both directions here. You get that V is both an upper bound and a lower bound, lower bound and upper bound. So, okay, anyhow. So you get S prime is a basis. All right. You can play the same game. Suppose that suppose you start with a set that covers the whole space. For example, the one we just talked about, right? We had V is equal to span of U1 to UN, right? That's what we had. Call this now S. And now we want to go down. We want to remove vectors. To get S prime Li. So you already have the span, but now you need to have linear independence. Suppose S is like, I don't know, 1, 0, 0, 1, and 1, 1. And then we go to S prime to be 1, 0, and 1, 1. Okay, that's one possibility. There's many ways to go. And do we talk about here? So let me see. What else was there here? I mean, this is not really done in your book, so I don't want to go too deep into it. But yeah, so you play the same game we just did. So yeah, so you have U1 to UN. This is your S, and then you ask the following question. You start from your very top, all of them, and you start removing one at a time. So you ask, is U1 in the span of U2 to UN? If yes, remove it. If no, keep it. Okay. And then same thing, U2, yes, no. So remove it or keep it. And the logic here is again that we have this lemma that it suffices to check the span being contained in the span to check for Li. Okay. All right. So here's the result that you're free to use. If you know that your V is finite dimensional, you can do the following. If you can give us some T that's Li, you can always assume that there's an extension to a basis. Conversely, if you know that S spans the space, you can always reduce it to a basis. So let me do like a Venn diagram. This is V, and this is S, and this is T. So you can grow T to be V, and you can shrink S to be V. Okay. All right. So you're free to use this result. All right. Yeah, I've been using this word many times. All it means, finite dimensional, is that you have a space V and you found a basis S. If it has finitely many elements, U1 to UN, then you call your space V finite dimensional, like R10 has 10 dimensions because 1 0 0 0 0 0 1 and then 0 all the way to 1 is a basis, and it has 10 elements. Okay, so R10 is finite dimensional. All right. Now we'll do more examples to get some more practice. And dimension. The definition of dimension is, again, the number of elements in your basis. Now recall last week we showed that if B1 and B2 are bases for same V, then B1 is equal to the size of B2. So silly example is take V to be R2, take B1 to be 1 0 and 0 1, and take B2 to be 1 0 1 1. They're both bases. They're not the same basis, but they're both same basis. They're both bases for same space. So for R2, and they both have the same number of elements. So it doesn't matter what V is out there. If you can find two different bases for it, they will always have the same number of elements. Okay, so this quantity here, dimension, is an invariant. So I'm not writing dimension BV, where B is a basis. I'm just writing dimension of V, because that's all the information you need. You don't need to know its basis, which is incredible if you think about it. Okay. And yeah, when you have infinitely many elements, like for example, take P of R, which is just the span of 1, x squared, so on. This guy has infinitely many elements in its basis. Can someone in the chat give me some other examples of infinite dimensional? I just want to see how comfortable you are with this stuff. Any other examples of infinite dimensional? That's right, that was one. So yeah, take any CK in your space. Yeah, starting from even 0. FR, what is FR? Oh, the functions, that's right, yes. Oh yeah, that's a very good example. Functions over your R, so FR to R, that's right. R infinity, yeah, that's another one. So these are the infinite sequences. X1, X2, so on.
Would you say when the basis has like infinite elements, like I think earlier you said a vector space with an infinite dimension like has no basis?
Right, so
So
yeah, no, good question. So how should I say this? So here we include both. So for example, let's go back to our example. So C01, space of continuous functions. This guy is actually uncountably, okay, let me not say this. What should I say? So this guy contains the following subspace. So that's one way you can answer this. So this guy contains the space of polynomials over 0, 1. So which is the span of 1, x, so on, but you take x in 0, 1, and the dimension of a space, we will prove it next, is less than the dimension of the bigger space. So take W to be these polynomials, and then take this guy to be our C01. And this guy here is infinite. So it implies that our bigger space is infinite. Now, that's why we don't use the word basis, because some spaces do not have a basis, like C01. So yeah, we will do this a little bit later, but yeah, there are ways to define dimension without resorting to the word basis.
Okay.
Yeah, I know what you mean, and it's tricky. But yeah, whenever you want to show something is infinite dimensional, because you cannot have a basis, you can use this relation that we're going to prove, that dimension of W is less than dimension of V, to prove that something is infinite dimension. So if somebody says, prove me like this stuff they wrote here are infinite dimensional, a very easy way to do it is find a guy that's countably dimensional, like this polynomials, where you have a basis, and then use this inequality to get infinite for both. Is that okay?
Yeah, thank you.
Yeah.
That makes sense.
Yeah, it's very tricky but there are definitions. You take like some sort of suprema over, but this is beyond our stuff. For now, all we need is to work with, with this basis. Okay. Oh yeah, I added the data analysis because I like data analysis. I do data analysis. Yeah, so I'll just speak briefly. Do I have time? Anyways, I mean, you can read more about this. It's called the curse of dimensionality. And basically, as you add more dimensions, your data set becomes harder to analyze. Yes, because they become more sparse. They're harder to cluster together. It's like somebody was saying, the weather, there's so many variables you can describe it, like temperature, humidity. You can go down the list. The more features you add, the more dimensions. So this is 1D, this is 2D, this will be 3D, and you get some crazy data set describing the weather. Let's say even location. I mean, that would be too much. Let's say weather at Toronto. And you have like maybe wind speed. So the more variables you add, let's say Toronto and even time, the harder it is to cluster your data together. So suppose each data set is like a day. Day 1, day 2, day 3. And you want to get some pattern of like, maybe this is winter, but it's like sunny now. Anyways, doesn't matter. So the point is, you can read more about this. Very interesting that adding more dimensions actually makes your data set harder to analyze because they start becoming more distant of each other. It's harder to cluster them. Okay, anyways. So let's prove the result I just talked about, that if you have a W subspace, so take W to be a subspace, and you know that it's inside some other space V, then you have the following relation for their dimensions. And moreover, if you have the equality, you could get that it's actually the whole space. So the interesting direction is this guy. The other one is not interesting, but the interesting is that if you have same dimensions, you have the same spaces. Now that's interesting. Just by doing a simple computation, you can get similar spaces. You don't even have to compute spans or anything. Anyways, it's amazing. Okay, so let's see. So we're gonna do this dimension thing, and I gave you some examples, and then it's the transformation, right? Okay. So let's do this dimension thing. All right. First, we show this inequality. Suppose by contradiction otherwise that you have strict, that it goes the other way. So you do the following. W is also finite dimensional. Remember, every subspace is a vector space. Every subspace is a vector. So you can play the same game. Every subspace is a vector space. So, you know, you have your span W1 to WM, and you can, yeah, so you have a basis W1 to WM. All right. So from all the stuff we just did. And we just defined the dimension of W to be the number of elements. So M is equal to dimension of W, which we said is bigger than V by contradiction. But we can play the same game, right? We proved this result that if you give me some Li set, so T is Li, because T is a basis. Well, now we can extend. We can extend to T prime. So it's a basis for W to get a basis for V. But we extend it, right? T is inside T prime. That was what we said. So that means you added more elements. You had to add more elements because W is inside V, right? So that was the contradiction, because we had to go from T to T prime, which contains T. So we had to add K more elements. So then we got the weird thing. We got dimension of V is M plus K, which we know to be dimension of W plus K, so bigger than dimension of W. Actually, this argument over here is even a shorter proof. You can just say this. I just wrote it in terms of contradiction for you, but if you can actually just do it just with this stuff. Yeah, exactly. So that's the one I just mentioned. Yeah. So you can even just use this argument over here. All right. And let's now finish up. Suppose that the dimensions are equal. Well, then in this thing we did, T, we extended to T prime, but then T prime will equal T. Okay, because there was no need to extend because their sizes are equal, right? So let me write a little bit. Let's just write it like this. So we know that size of T is M. Suppose that T prime size is bigger than M, okay? But this is, but we built T prime to be a basis for V. So size of T prime is also M. So that means we made no addition. So we have W is span of T, which is span of T prime, which is V. So indeed, W is V. right? So we made no addition. We kept the same T prime because we require to have M elements. And then we use the relation W is span of T. And we know T is T prime. So this is span of T prime, which the augmentation process tells you that this is V. Okay. All right. Thank you so much. I'll see you tomorrow, guys. Thank you.
Hello, Professor.
Yes. Hello.
I know that the midterm is in 2 weeks.
Mhm.
And I'm really struggling to use the knowledge put in the text, like
Uh-huh.
because there's a lot of like proofs and everything. I'm not sure what to learn and what to understand. So do you think like if I really learn all the proofs in the slides and understand them, will it be enough? Plus the exercises that I do in the text course.
So your priority should be as follows. So number one, it should be all the homeworks, quizzes, and suggested problems. So what do I mean by that? So we gave you some quiz, right? Reading quiz, whatever. You go look at it and you're like, oh, I don't know how to do this. But it's still, the quiz is still about something from the course material, right? It would be like, show something is a subspace, right? Hello?
Yes.
Yeah, so then you go to the relevant section where like definitely start from our class notes. So start from class notes because we try to trickle it down. Like we have a plan. We don't cover everything from the book. And first go to the class notes and see, okay, does this help me answer the question of, so this W is a subspace? If yes, good. If no, then go to the book and try to figure out, read some of the examples. But just to be clear, what I'm saying is always start from what you've been assigned. And then work backwards to see, okay, what do I need to answer this question?
Okay, I see. And for the successes problems, I know there are some corrected problems on the back of the book, but not all of them are corrected.
There's some I don't sorry, what? There's some what?
For the suggested problems, like sometimes I want to check if my answer is correct or not.
Uh-huh.
I can check at the end of the textbook, there's a part where some exercises, some questions are corrected, and there's the answer, and some of them there's not.
Right. You can come to Piazza. Just post your stuff on Piazza.
Okay.
Yeah.
I see.
Yeah.
Okay, I see. So I just asked what answer for
no post like you work on a question.
Yeah.
And put like a screenshot.
Yeah.
Oh, this is what I tried. This is my answer. Is this correct? This is not correct, and we can help you.
Okay.
Like we can go through your answer and say, okay, this is right or this is wrong.
Okay, I see.
Yeah.
Well, thank you so much. Well, and last thing, it's about closure under multiplication.
Mhm.
For example, when they say that the scalar C, belongs to a field F.
Uh-huh.
What's the field F exactly? Is the field F is the set, like are we that we are testing for multiplication closure or what?
Okay, so I'm not sure
okay, I'll repeat my question.
So is this closure for a vector space or what?
Yeah, a vector space. Yeah.
Yeah, okay. So for vector space, right?
Yeah.
Every vector space comes with a field.
Yeah.
Comes
But
with.
but honestly, which field to choose? Because
No, you don't get to choose it.
there are fields
No,
you
no,
want
you
to
don't get to
factor in.
choose it. You don't get to choose it. It's abstract. So
Okay.
so we covered it in like week 1. It was like an abstract object,
Yeah.
and you don't get to pick it. Like when the question, like in homework 1,
Yeah.
there was a question with some V space.
Modu- Oh yeah. Yeah.
No. Just it was like I'm talking
Yeah.
about the
Question three about defining the addition and
no. There was a question with it was like V and union W is a subspace.
Oh yeah. Yeah. Yeah.
Yeah. So here, the field is abstract. So
Okay.
when they ask you to show that this guy is a subspace, you have
Yeah.
to check closure with respect to Cx plus Y being in
Yeah.
VW for C in the field, in some
Okay.
field. It could be the reals, it could be complex numbers, it could be F3, doesn't matter. This
I see. I
Yeah.
see. Yeah. And last thing, it's about the axioms of the field. I saw a symbol that I didn't understand, and it's not in the book that you gave us. Wait a minute. I'll type it to you. It's something like LX. It's like I typed it in the chat.
It was in the book or in my notes?
In the book. In the book.
Which page?
I sent you the symbol on the chat on the Zoom
Yeah,
chat.
but I don't know what LX means. Which page was it?
Oh, I forgot. It's about the axioms of a field. It's the 9th axiom. It's in the beginning. It's like 10 something.
So fields are covered in 234.
Yeah, 1-1. It's in 1-1-1.
Okay, that's not because they don't do fields in chapter 1.
Oh, really?
No, they don't. So 1-1. I am in 1-1. Then
Wait a minute. I'm opening the book.
there's no 9. So I don't know. It could have been 1x. Oh yeah. Thank you, Zachary. No, 1x is okay. Yeah. First of all, let's make sure that I think that's the one Zachary said. So yeah, one of the field is just the additive identity, or no, multiplicative identity. So
Okay.
so that means it's like the one in the real numbers, like 1f times
Okay,
x
yeah, understood.
is x.
Yeah, because it looked a bit weird.
Yeah, because it's not one for real. Like it could for the when f is r, 1f is 1. When f is the complex numbers, 1f is okay, it's again 1. Let's see, what's another example? Usually it's always 1. I have to think hard to find some example where it won't be 1.
Wait a minute. Okay, I found the page. It's page
no, I think I know this is it's just the 1f that Zachary said.
Okay.
Right? Like, okay,
Oh
what's
yes, yeah. It makes sense now. It makes sense.
Okay.
Yeah. Thank you so much.
Yep.
Have a nice day.
I had a question from the
So who are you?
Rudraksh.
Okay, yeah.
I had a question from the the class reflection quiz from last week.
Okay.
Why exactly is the span of x and x squared? Oh, why exactly is the set? Wait, I gotta check the question. 1 second. Right, why is the set x comma x squared linearly dependent?
Oh, right. That was my question. X comma
Yeah, that was the week 3 reflection quiz.
X comma X. Oh, yeah, right. So, yes, X comma X squared. Then you had the field was 0, 1, 2 or what?
It just said the set S equals x comma x squared subset of P2 F2.
F2, right. So it's just 0, 1. Right. So let's check independence. So what does it mean to be independent?
Wait, well, what does it mean when it's a field of P2 of F2? Does it mean like polynomials?
Yeah. So, but let's start with the simple. Like, what does it mean to be independent? These two guys.
That if you take any linear combination of them and set it to equal 0,
Yeah. Let's do it. Tell me. Yeah.
coefficients must equal 0.
Yeah. Tell me what to write down.
So ax plus bx squared equals 0.
For all x
Yeah.
in the field. But then here you have two elements. You will only have 0 and 1. So you have A times 0, B times 0, which is 0. So there's no information here. And you also have A times 1 plus B times 1 equal 0.
Mhm.
And so what did I want to x squared f2, is this f2?
Yeah, that is F2.
Okay, then and I
But,
said dependent.
Polynomials of degree.
Oh yeah, and it was false, right? Right, this is
Yeah, it
false
was
because you get you see from here right. So yeah, so it's false because you can just set a to be minus b and you get this guy to be 0. So whereas to have li, you needed a to be b to be 0. But here I can just take a to be 1 and b to be minus 1. And I get 1x plus minus 1x squared to be 0 for all x in this field, not in general, like not in the real numbers, just in this f2 guy.
But then what does it mean when it says P2 bracket F2?
Sorry, what?
The question said that the set x comma x squared is a subset of all.
Yeah, I mean, this is, I thought it was in the book as well, but we talked about it. Like in general, when you write P2F, these are all the polynomials.
Oh,
A0.
so A can be from F2, that means.
Yeah, A1
see, okay.
x, A2 x squared, where you take the AI from the field and the x from the field. Yeah.
I see, okay.
Yeah.
Okay, thank you.
Yeah. Any more? Yeah, just you can talk. Yeah.
Sure. Hi, Professor. I have a question. It's not exactly regarding what we're studying, but it's algebra, and I don't know who else to ask.
Sure. Yeah.
So if you have a matrix and you want to decompose it into a product of 3 matrices, where like the middle one is like just a diagonal matrix that has the eigenvalues in the diagonal, how do you find the two like outer ones? How am I supposed to find that?
Wait, is this for something else? For some?
It's for my physics class, but no one taught.
Oh, I
no
see.
one taught us.
No,
So
we
I don't know how to...
No, I mean, this is, you should talk to your prof because I mean, yeah, also here, but like P are just the eigenvectors. We talked about it in week 1. So you find the you form the columns out of the eigenvectors of M, if it's like diagonalizable. I'm assuming that it's diagonalizable.
Well, they said it's, yeah, they said it is, like, yeah, like.
Yeah, so
we
then if it is, it means you can find eigenvectors. So, M of Vi is lambda I Vi. And
And then you just like invert it to get the inverse P. Just regarding how do we know which one is P and then which one's P inverse? So the P
no,
is
the way I
leftmost
think
one?
this is the correct way I wrote it. And how would you see that?
Like, yeah, how do I just like memorize that the one with the eigenvectors is the leftmost one?
No, there's no, okay, there's logic to this. So let me see, just a second. Oh yeah, here's how you can memorize it if you like. So M acts on, let's pretend, because this is like a change of basis, so
That's fine. We can talk about that. So like, if I assume that like we're in some basis, does P inverse take you to the eigenbasis and then P takes you back to your normal basis after D does the whatever transformation? So like, I don't know if I can annotate.
no, that's exactly the idea, because M acts on, let's pretend, standard
Some P.
basis,
Yeah, okay, yeah, sure.
or I don't know, I mean, but it acts on the standard basis stuff, and then P inverse, yeah, takes you away into the V stuff. You act with your D, and then P acts on this V, and it takes you back to some E guy.
So the matrix that takes you from the eigenbasis to whatever initial basis, that's the one with the eigenvectors? Is that the?
Yeah.
Oh,
But
okay.
but it's a little bit okay. Well, I mean, we'll come back to this like a million times because this is the main point of the course. But
Oh, it is? Okay.
But yeah, so yeah, we'll come back. But
Okay.
I mean, yeah, okay. But you can see this if you want to read it for your course. This is done in, I don't know. Yeah, you should be able to which chapter? Yeah, you can go to our chapter 4 and
Chapter 4, okay.
yeah, of course. And I think the stuff I'm talking about are done in spectral theorem. If you want to read ahead. Where is it?
I mean, it's okay. I'm sure I can find it in chapter 4. I don't need you to like, it's fine.
Yeah, it's weird, right? There's not much. What about no, I know, because like I did a bit of physics. I remember I needed what about in the notes I uploaded? Are they there? Let me check. So I uploaded some change
Which
of
one? Because
basis.
you talked about it in week
Yeah,
1.
just a
but to
second,
be
because I
honest,
uploaded if you go under my section, I uploaded some notes. Okay.
Okay.
So yeah, diagonalization. So if you go under my section,
Oh yeah, diagonalization and the change of basis, I see.
and then, but do I talk about, yeah, and I also have this P inverse, and yeah, okay, whatever. You can read it there. So,
Yeah, it's okay. Thank you so much. It is very helpful. Thank you. All right, have a great day.
okay.